Hello. In the previous lecture, we were studying system of polynomial equations. We were trying to find a single solution for such a system of polynomial equations under the assumption that these polynomials do not generate the entire ring of polynomials. We wanted to proceed by induction on the number of variables with having the elimination process in mind. We studied, and this was the setting that we were working with, so we were assuming that I is an ideal of the ring of polynomials in n variables. Then, by eliminating the variable x sub n, we considered the set of polynomials inside I that do not have the variable x sub n, which means this intersection. Now, assuming that by the induction process, by the induction hypothesis, we can actually find a zero of this system of equations. So assuming that I have some element over here, we wanted to see if we can find a solution for I with the first n-1 components being equal to these A. So essentially, we have this projection map from the common zeros of I to common zeros of I intersected with ring of polynomials with variables x sub 1 x sub n-1, and we wanted to see if this is a surjective map. We worked under the assumption that this is not surjective, and we showed the following important lemma. We defined resultant of polynomials and used that to show this important lemma. So the lemma says that if f is algebraically closed, and A is a zero of those polynomials of I that do not have x sub n in them. And let's assume that there is no common zero. There is no common zero of I that starts with a1 a sub n-1. Under these assumptions, we showed for every g inside I, if I view g as a polynomial in terms of x sub n, write it like this. I think I used the degree m for g. So this, for every g inside I, if I write down the coefficients like this and I assume that these coefficients are inside the ring of polynomials with variables x1 x sub n-1, then for every such g, the leading coefficient, so and gm is the leading coefficient, then the leading coefficient evaluated at A is actually 0. So this is an important lemma that we proved using resultant of two polynomials and the fact that if f and g are two polynomials in a bracket x, then the resultant of f and g is both inside A and in the ideal generated by f and g. So we use this in order to prove the previous lemma. Now, next, what we wanted to do was to show that after a linear change of coordinates, we can guarantee existence of a polynomial with constant non-zero leading coefficient, which clearly implies that this conclusion of this lemma cannot hold. Conclusion of this lemma says that the leading coefficient evaluated at A is supposed to be 0. If I tell you that the leading coefficient is indeed a constant polynomial, then it can never be 0. Because this conclusion fails, that means that the hypothesis cannot hold, which means pi, in that case, would be surjective. Which means having a 0 for this set of equations, we can end up finding a 0 for I. And that's exactly what we want to show, finding a 0 for the ideal I. Okay, so we were in this setting. Now let's go back to my notes. This was just a recall on what we were doing. And so let's recall how we wanted to produce this polynomial with a constant leading coefficient. So our key tool was these functions, theta of a's. So this was the linear change of coordinates that we had considered. So essentially we go from x1 dot xn to x1 minus a scalar multiple of xn, x2 minus another scalar multiple of xn, and so on. We do not change the last entry, x sub n stays the same. We showed that if I parameterize this map by the scalars that we are multiplying, we showed that a composite of theta sub a and theta sub b is the same as theta sub a plus b. From there, we can deduce that both, theta of a is inverse of theta negative a, and therefore these are bijective functions. And considering that these functions are composite of this linear change of coordinates and the evaluation, we can check that it is indeed a ring homomorphism and it is F-linear. Now, because it's F-linear and it's a ring homomorphism, it's enough to understand what this map does to monomials. Now, for a monomial, we say its total degree is sum of the degrees of each one of the variables that appear. So if x1, the power of x1 is I sub 1, power of x2 is I sub 2, and so on, the total degree of this monomial is defined to be sum of the powers. Now, I'm going to partially order all the monomials that appear in a given polynomial H, and then I take the maximum total degrees that appear. There might be many monomials with the same maximal total degree. I put all of them together and call that one H bar. So for a non-zero polynomial H, I'm going to let H bar be the polynomial with where all the terms of H bar have the maximum possible total degrees among all the monomials of H. And so that means that all the monomials in E have a smaller total degree. Okay, but let's go back to theta of A and try to understand what theta of A does to a monomial like this. So I give this monomial to theta of A. By definition, theta of A, since this monomial, I have to evaluate it at the point where the first component is x1 minus a sub 1 xn. The second one is x2 minus a sub 2 xn, and so on. So this means I have to take x sub j minus a sub j xn and raise this to power I sub j as j runs from 1 to n minus 1, and the last term doesn't change. The last term is xn to power I sub n. So theta sub a of this monomial is this. Now if I use the binomial expansion and expand it, I realize that, and view it as a binomial in terms of x sub n, I realize that the largest degree of x sub n in this binomial is x sub n raised to power I sub j, and it appears with coefficient negative a sub j raised to power I sub j. Now I'm multiplying all these terms, so I end up getting summation of I sub j's as the power of x sub n, and the leading coefficient would be the product of these elements, a sub j raised to power I sub j. Remember, a sub j's are inside the field F. So altogether, we end up getting this element inside F times x sub n raised to power m, and m is the total degree. The other terms, if I view it as a binomial in terms of x sub n, the other terms would have smaller degree. So these r sub i's are indeed polynomials with variables x sub 1 dot x sub n minus 1. And the key point being that the leading coefficient is actually a constant, a non-zero constant. But the other variables, the other coefficients, they might be polynomials, and we are not interested in understanding them, but we are interested in saying that the leading coefficient is indeed a non-zero constant. Now, this happens to each one of the monomials, and this power is precisely the total degree of this monomial. It is also useful to notice that this number that we have over here is evaluation of the monomial that we have at the vector a. So if at the vector negative a. So if I evaluate this monomial at negative a, I get this leading coefficient. Now, when I apply theta of a to summation, a linear combination of these monomials, which means an arbitrary polynomial, we get summation or linear combination of these polynomials. And we see that the leading coefficient would be, okay, so in the coefficient of x to the n raised to power the total degree of the monomials. Now it depends on the monomials that appear that have the same total degree. So that's why we are going to gather all the monomials that have the maximum total degree. So suppose m is the maximum total degree of among the monomials that appear inside H. And let H bar be that part of H, summation of those monomials of H that have the same total degree, and their total degree is this maximum m. So it's the sum of all the monomials that have total degree m. So the other monomials of H have total degree less than m, and I put them in the polynomial E. Now I apply theta of A to H. Because theta of A is a ring homomorphism, theta of H is theta sub A of H bar plus theta sub A of E. Now notice that every element that appears over here is going to have, if I view it as a polynomial in terms of x sub n, is going to have degree strictly less than n, because all the monomials have total degree strictly less than n. Now, if I manage to make sure that this polynomial, the h bar part, gives us a polynomial of degree m, then that would be the leading coefficient if I view it as a polynomial of, in terms of x sub n. But by this discussion, by this one, we know that each one of the monomials is mapped to a polynomial of degree m with leading coefficient, which is essentially evaluation of the monomial at negative a. So now I'm taking linear combinations of them. So altogether, we end up getting h bar evaluated at negative a as a possible leading coefficient for x sub n raised to power m for this polynomial. So when I say a possible leading coefficient is because I have to make sure that this is non-zero. So if I manage to show there exists some a for which this is not zero, then we end up getting a polynomial which has a non-zero constant leading coefficient for x sub n raised to power m, for x sub n. So this polynomial, this polynomial is of smaller degree, or degree less than n. And coefficients are inside the ring of polynomials with variables exponented at x sub n minus 1. But the key point is that if I think about it as a polynomial of x sub n, then its degree is less than m. So it's not going to make any problem for us as long as we manage to show that for some a, this is not zero. So next, we are going to show an easy claim that if I give you a polynomial, a non-zero polynomial, then a non-zero multivariable polynomial, then over an infinite field, you can always find some value, some vector, where the value of this polynomial is not zero. Okay, so let's see what the claim is, and let's try to prove this. So this is not what I wanted to see. Okay. So this is the claim. If f is an infinite field, and I give you a non-zero polynomial, then for some a, the value of this polynomial cannot be zero. We are going to prove this by induction on the number of variables. If I have only one variable, then we know that the number of zeros of a non-zero polynomial of degree d is at most d. So this means that I cannot have infinitely many zeros. And because f is an infinite field, we deduce that h is not zero for some a inside the field. Okay, so that's for single variable case. Now let's do the induction step. I'm going to write down my polynomial h bar in terms of x sub n. So that means h bar is some polynomial in terms of the lower indices variables, x sub n to power m, and so on. Now, what I will do, I will make sure that when I evaluate these h bar, when I substitute the first n minus 1 entries by some vector from f to n minus 1, we end up getting a non-zero polynomial in terms of x sub n. Then, if I manage to do that, then I'm in the realm of single variable polynomials, and we can be done by this problem. In order to make sure that after evaluation of h bar, I do not get the zero polynomial, it's enough to make sure that the leading coefficient is not mapped to zero, is not evaluated to zero. That's exactly the induction hypothesis. Okay, so let's make all the steps precise. So because h sub m is not zero, and it is in the polynomial, a ring of polynomials with n minus 1 variables, by the induction hypothesis, there exists some vector a, some n minus 1 tuple a1 dot a sub n minus 1, so that the leading coefficient evaluated at this is not zero. Now I'm going to evaluate my polynomial h bar at this n minus 1 tuple, and that means I'm substituting a sub i's for x sub i's, and of course the last variable is not touched. So we end up getting this polynomial where the leading coefficient, now we know for sure, is not zero. So we end up getting a polynomial in f bracket x sub n, and the degree of this polynomial is m. It's a non-zero polynomial. That's the key. Now I'm giving you a non-zero single variable polynomial, and we have proved that non-zero single variable polynomials over an infinite field, if I view them as functions, they are non-zero functions. So that means that I can always find some element, a sub n, and plug in and get something non-zero. Okay, so again, when I evaluate it, I get a non-zero single variable polynomial, and because f is infinite, we can find some a sub n and add it to the ones that we have already found and make sure that h bar is giving us a non-zero value. Okay, so this shows the claim. Now we can go back and use our computation over here. Over here, we have made this computation that when I when I apply theta sub a to h, not evaluate, when I apply this isomorphism to h, I end up getting a polynomial in terms of x sub n, where the leading coefficient is evaluation of h bar at negative a, where h bar is that part of h that, that consists of summation of monomials with maximum total degree. Now, this is a non-zero polynomial. With the claim that we showed, we can always find a so that this is non-zero, and that's exactly what we claimed. So this is a dilemma that we wanted to prove. We wanted to show that there is a, so that this is a polynomial of this form where c is a non-zero unit, is a non-zero constant. Okay, so now let's see how this can help us to get 1, 0 for one common zero for the ideal I. This is called Hilbert's Nullstellensatz. Okay, so what is this statement? Suppose F is algebraically closed. So it's a field, it's algebraically closed. Suppose I is an ideal of the ring of polynomials with n variables. Then polynomials in I, have a common zero if and only if it is a proper ideal. So again, z of I is not empty. We can find a common zero for all the polynomials of I precisely when I is a proper ideal. 1 does not belong to I. Okay, so if 1 is inside I, of course there is no zero. 1 is constant, it's never zero, so there is no common zero. So this direction is easy. Now the whole point is the other way around. And we are going to proceed by induction as we suggested. The base case is again easy. When n is 1, I'm dealing with a PID, then every ideal is principal. And because I'm assuming I is a proper ideal, P is not a unit, so it's either 0 or a larger degree or non-constant polynomial. And because F is algebraically closed, every non-constant polynomial has a 0 in F. So if P is 0, we already have the answer, because then the common zeros of 0 is the entire field. So there, for sure, Z of I is not 0, is not empty. Now, if P is a non-constant polynomial, because F is algebraically closed, we can find some A1, which is a 0 of P. And because the I is an ideal that's generated by P, and P and A1 is a 0 of P, we end up getting that A1 is a 0 of the ideal generated by P, which is I. Okay, so we are done with the base case of induction. Let's go to the induction step. Now, in the induction step, we want to project to the first n-1 components and use induction hypothesis. But in order to do so, I need this. I need to make sure that there is some element where there is some element inside the ideal where the leading coefficient is a non-zero constant. Okay, so that's what we do using the previous lemma. By the previous lemma, there exists some vector inside f to the n-1 such that when I apply the isomorphism theta sub a to h, so again, let's make sure that I say what h is. So if I is 0, then we are done. Assume that I is not 0. In that case, I can find some polynomial inside I, which is not constant. So again, we are assuming that z of I, we are assuming that I is a proper ideal, which means I does not contain any unit. That means any non-zero constant is not inside I. Now, I'm also assuming that I is not 0. That means I do have some polynomial that is not constant and is inside I. Okay. Okay, so now I pick this h, and then by the previous lemma, I can find some a and apply this isomorphism theta of a to h and end up getting a polynomial of this form where c is a constant polynomial. H sub i's are multivariable polynomials with variables x1 to the dot x sub n-1, but the leading coefficient c is a constant polynomial, is a unit inside f. Okay, so now how can this help us? Because this is an isomorphism, when I apply it to the ideal I still get an ideal. Okay, so this is an ideal of this. But how does this help us? The key point is the connection between common zeros of this ideal and common zeros of I. Remember, after all, this is coming out of a linear change of coordinates. So when I give you a common zero of this, let's try to understand what it means. It means for every f that you give me inside the ideal I, if first I'm going to apply theta of a, and then evaluate it at bi's, and I am supposed to get 0. But what is this evaluated at bi's? It is f evaluated at b1 minus a1 times the last entry, a1 times bn, b2 minus a sub 2 times bn, dot b sub n minus 1 minus a sub n minus 1 times bn, and the last entry is not changed. So all of a sudden, we are getting a common zero for all the elements inside I. So altogether, we are getting that B belongs to zeros of theta sub A of I precisely when this vector is a common zero of I. this is a bijection between zeros of these two ideals. In particular, we do find a common zero for all the polynomials inside I if and only if we find a common zero for all the polynomials in the ideal theta of A applied to I. Okay, so then in order to show this ideal is not empty, it's enough to show this ideal is not empty. So that's what I'm going to focus on. Now, because I do have a polynomial where the leading coefficient is constant inside this ideal, we deduce that the projection to the first n-1 components is indeed surjective. So again, this is precisely the lemma that we proved in the previous lecture, that if the projection fails to be surjective, then there should not be any polynomial inside this ideal with non-zero constant leading coefficients. Okay, so now because of that lemma, we deduce that this is a surjective map. Now notice, because 1 does not belong to I, 1 does not belong to theta sub A of I. Theta sub A is an isomorphism after all. And because 1 does not belong to this ideal, of course it does not belong to the intersection of this ideal with a subring that we are given over here. So that means this is a proper ideal of the ring of polynomials with one less number of variables. So I'm allowed to use the induction hypothesis for this ideal and get a common zero for all the polynomials inside this ideal. So again, by the induction hypothesis, we obtain a common zero, b1 dot b sub n minus 1, for the ideal theta of A intersected with the ring of polynomials with one less number of variables. Okay, so this is a common zero of this ideal. Now, as I pointed out, this map is surjective because of the important lemma that we proved. Again, because theta of A has an element of the form c times x sub n raised to power m plus the rest, and c is a unit, is a constant polynomial, by the lemma that we showed, we can deduce that pi is surjective. Okay, that means we can, this is in the image of pi, which means there exists b1 dot b sub n in the common zeros of theta of A of I. In particular, this is a non-empty set, and therefore z of I is a non-empty set. And that completes the proof. So now we know what Hilbert's Nullstellensatz theorem is. Now, this theorem has many implications. For instance, we can use this to classify all maximal ideals of the ring of polynomials in n variables when f is algebraically closed. But for n equals to 1, let's quickly recall that an ideal of ring of polynomials with one variable is maximal if and only if it is generated by an irreducible polynomial. This is the case because it's a PID. For PIDs, we showed that an ideal is maximal if and only if it is generated by an irreducible polynomial. But f is algebraically closed, so irreducible polynomials are of degree 1. Every polynomial can be split, can be decomposed into product of degree 1 polynomials, so irreducible polynomials are of degree 1. And because ideals are generated by monic polynomials, essentially we deduce that every maximal ideal of f bracket x is of the form x minus a for some a inside f. So altogether, we get a bijection between f and maximal ideals of f bracket x. Hilbert's Nullstellensatz implies the same statement for multivariable setting. And we call this statement the second version of Hilbert's Nullstellensatz. Okay, what is the statement? Assume f is algebraically closed. Then the following is a bijection. Given a point inside f to the n, I'm going to give you a maximal ideal of the ring of polynomials in n variable. And what is it? Starting with the vector a1 dot a sub n, I look at x1 minus a1, x2 minus a2, xn minus an, and I look at the ideal generated by this. Claim this is a maximal ideal. This ideal, every maximal ideal is of this form. And moreover, this ideal is precisely those polynomials, consists of those polynomials that vanish at the point A. Okay, so now again, this second version of Hilbert's Nullstellensatz gives us a bijection between the points of f to the n and maximal ideals of ring of polynomials in n variables. And this bijection is very concrete. Given a point, we look at all the polynomials that vanish at this point, and that would be a maximal ideal, and every maximal ideal is of this form. And indeed, we have a concrete generating set for this ideal as well, and this ideal is generated by xi minus a sub i's. Okay, so let's see how the proof goes. Similar to the single variable case, we start with the evaluation map. So given a inside f to the n, we look at the evaluation map from the ring of polynomials in n variables to f. Okay, so this is a surjective ring homomorphism. Because the constant polynomials are sent to themselves, this is a surjective ring homomorphism. This is f linear as well. So if I use the first isomorphism theorem, we deduce that the ring of polynomials mod out by the kernel of this ring homomorphism is isomorphic to its image, which is the codomain f. So this quotient is a field. Now we know quotient of a ring by an ideal is a field if and only if the ideal is a maximal ideal. So from here we deduce kernel of this evaluation map is a maximal ideal of the ring of polynomials in n variables. Next we show this kernel is precisely this ideal. Notice that this kernel by definition is all the polynomials that vanish at the point A. So these are the same things. So saying that it is kernel of phi sub A is the same as saying that it is I of the set A bar, A hat, and the vector A. Now, the first thing that we notice is that when I evaluate x sub I minus a sub I at this vector, I end up getting 0. So all of these guys are in the kernel. In particular, the ideal generated by x sub I minus a sub I is a subset of the kernel. Now I can finish the proof of equality in different ways. For instance, I can notice that the leading coefficients of these, x1, xn, these are the leading coefficients, and every monomial is a multiple of one of these. So for sure, the leading coefficients of these generators generate every leading coefficient. And therefore, notice that this is a proper ideal, and therefore x sub i's generate every leading coefficient. So therefore, by a result that we proved in the previous lecture, these things should generate this ideal. This is one way, but a more concrete way is first we divide by x1 minus a sub 1. Notice that this is a monic polynomial, so I am allowed to divide by this. So I divide by this, and the remainder would be a constant polynomial in terms of x sub 1, which means it will contain, okay, so I have started with x sub 1. Let's say I divide by this one, and the remainder would be evaluation of this polynomial at a sub n. Here I'm viewing all the polynomials at polynomials in terms of x sub n. And the rest I put in the ring of coefficients. So by a result that we proved long ago, whenever you divide a polynomial by x minus a, the remainder is evaluation of f at a. So we get the quotient plus evaluation of f at a sub n. So these coefficients we do not touch. Now I repeat this for this polynomial in terms of x sub n minus 1, then in terms of x sub n minus 2, and we continue like that. We end up getting that f is a multiple of x sub n minus a sub n, a multiple of x sub n minus 1 minus a sub n minus 1, and what remains is the value of f at the point a. But the assumption is that f is inside the kernel. That means I'm assuming f evaluation of f at a is actually 0, which means this term disappears, and I end up getting that f is in the ideal generated by x sub n minus a sub n, x sub n minus 1 minus a sub n minus 1, dot x1 minus a sub 1. So that shows equality of these two ideals. So that means that this moreover part is proved now. So this moreover part is now proved. And we have proved that this is a maximal ideal. Now here is the crucial important part. Okay, so maybe before the crucial part, let's also discuss why it is injective. Injectivity now it's actually straightforward. Why? Because of the way that we showed it. I mean, so, or I can use like this. Then I say that if I look at the common zeros of this, okay, what do I get? This is supposed to be 0. That means x sub 1 is supposed to be a sub 1. The next one is supposed to be 0. The second component is supposed to be a sub 2. The last one is supposed to be 0. The last component is supposed to be a sub n. So it has only one common zero. So notice that this is indeed a common zero of all of them. So this means that the common zeros of this ideal is a single point, and that is a. In particular, if I tell you that two of these ideals are equal, you can deduce that these a sub i's are giving me the same vector. So that shows that this function that we are given, this function, is injective. Now, so injectivity and well-definedness were not that hard. What is crucial is why it is surjective. This is often the case in mathematics. Proving a function is surjective is much harder. Okay, how can we show it's surjective? So we start with some maximal ideal, and I need to show that it is of the form common zeros, all the polynomials that vanish at a given point. Okay, but how can I get that? The point is that M, because it's maximal, is a proper ideal. So I can use Hilbert's Nullstellensatz, the first version, and deduce that M has a common zero. So there exists some A that's a common zero of all the polynomials of this maximal ideal. That means M is a subset of all the polynomials that vanish at this point A. M is a maximal ideal. This is a proper ideal. So they should be equal. So this is a proper ideal, and M is a maximal ideal, which is contained inside this proper ideal. So I need to have equality. And that's exactly what we wanted to show. So we showed that every maximal ideal is of this form. Remember, this is precisely kernel of evaluation at A, and this is exactly this. So altogether, we get that every maximal ideal is of this form, which means that this map is also surjective. Okay, so now we can use this bijection between f to the n and maximal ideals of the ring of polynomials to give a bijection between points, common zeros of a given ideal and maximal ideal of the quotient ring. So that's called, again, Hilbert's Nullstellensatz, but let's call it the third version. So again, F is algebraically closed. We are given a proper ideal of the ring of polynomials. Then the following maps are bijections. So we pick a zero, a common zero of this ideal. So there is a bijection between common zeros of these ideals and those maximal ideals of the ring of polynomials that contain I as a subset. Sometimes we call them maximal divisors of I. And moreover, there is a bijection between this set and maximal ideals of the quotient of the ring of polynomials by the ideal I. So altogether, we get a bijection between zeros of I, common zeros of the ideal I, and maximal ideals of the quotient ring. Okay. So what are the maps? So the map is similar to the previous theorem, previous version of Hilbert's Nullstellensatz. Given A, I send it to all the polynomials that vanish at A. And we show that this is precisely the ideal that consists of all the polynomials that vanish at A. And this map is the usual, is the map that comes from the correspondence theorem, that every ideal of this quotient is of the form some ideal that contains I modeled by I. So using the correspondence theorem, we immediately get this bijection over here. So I'm not going to discuss this part of the theorem, and I will focus only on the first part. So clearly, there is a bijection between those maximal ideals that contain I and maximal ideals of the quotient ring. So the content of this Hilbert's Nullstellensatz version 3 is on this part, that there is a bijection between zeros of I and maximal divisors of I. Okay, so let's see how the proof goes. So I give you a point, that's a common zero of I. Now, that means I consists of polynomials that vanish at the point A. Now, by Hilbert's Nullstellensatz, we know this is a maximal ideal and it is of the form, it is generated by x sub I minus a sub I. So it is generated by this and it is a maximal ideal. So this means the map that I am giving you is indeed well defined, because this maximal ideal contains I. So this means the map that sends A to this maximal ideal is is indeed a well-defined map, because I'm sending A to a maximal ideal that contains I. Okay, because the function that sends A to this ideal is injective, even if A is chosen from, even if A is an arbitrary point inside F to the N, we know that this is an injective map. So automatically this map is injective after I restrict A only to the common zeros of polynomials of I. So injectivity is not a problem. So far we have showed it is well defined. Now we show that it is injective. Let's go to surjectivity. So suppose I give you a maximal ideal and I assume that I is a subset of M. By the second version of Hilbert's Nullstellensatz, we know that this maximal ideal is the set of common zeros, is the set of all the polynomials that vanish at some point. Now, I is supposed to be a subset of this. What does that mean? This means every element of I every element vanishes at A. That means A is a common zero of all the elements of I. That's exactly what we wanted to show. So altogether, we are getting that every maximal ideal that contains I is of the form I of a point that's a common zero of all the polynomials of I, which shows that the map that we are given is indeed surjective. So we show that it is surjective, it is injective, and that implies that it is a bijection. The second part, as I've indicated, as I've mentioned earlier, is an immediate corollary of the correspondence theorem between ideals of a quotient ring and ideals of the larger, the mother ring that contain the given ideal I. So again, ideals of A over I are of the form J over I, where J contains I. Okay, so now we have seen three versions of Hilbert's Nullstellensatz. And there is another version of Hilbert's Nullstellensatz, and that would be our final version that we discuss. And this version gives us a full understanding of all the polynomials that vanish on the set of common zeros of a given ideal. So again, let's try to understand it. I give you an ideal I. Then you look at all the common zeros of the polynomials inside I. Ask yourself, what are the polynomials that vanish on the entire set Z of I? So that means, what can I say about elements inside I of Z of I? What are the polynomials that vanish on the set of common zeros of elements of I? Okay, so one observation is the following. If I tell you f raised to power m for some integer m is inside I, that means f to the m restricted to the common zeros of I is 0, because f to the m is inside I. But that is f restricted to z sub I raised to power m. In a field, there is no nilpotent element. If some element raised to power m is 0, then it is 0. So this means if I tell you f to the m is inside I, then f vanishes on the set of zeros of I. So altogether, we are getting that all the polynomials that after raising to some positive integer ends up being inside I, all these polynomials are subsets of I of Z of I. So this set is denoted by radical of I, and we call it the radical of this ideal. Okay, so when I is the zero ideal, for instance, so it means what are the polynomial, what are the elements that I get, what are the elements that after raising to power m ends up being 0. So that's exactly the nilpotent, and the set that consists of nilpotent elements of this whatever ring that I give you. So this definition is for radical of an ideal, not necessarily inside this ring. For any unital commutative ring, I can use this definition and define radical of I. Radical of I in any unital commutative ring is indeed an ideal, and there are many interesting properties for this. But let's focus on Hilbert's Nullstellensatz. So the final version of Hilbert's Nullstellensatz says that if f is algebraically closed and I is an ideal, then I of Z of I is precisely radical of I. So this is an important result. So even the particular case of this, when I is a prime ideal, is of interest, because in that case we get the radical of a prime. We will discuss it later, and we will see radical of a prime ideal is itself. So that means that I of Z of P, where P is a prime ideal, is P itself. So we get a correspondence between common zeros of a prime ideal and prime ideals. We get this by induction. Okay, so now let's try to prove this result. We have already discussed that radical of I is a subset of I of Z of I. Now we want to show the other way around. We are going to use a trick that's called Rabinovich trick. Okay, so what is it? Let's try to think on what we want to do, and the trick comes to us. We want to say that if f is not inside the radical, then it is not inside I of z of I. Okay, what does that mean? What does it mean that f is not inside this? It means I should be able to find a common zero for the elements of the ideal, which is not a zero of f. So we should be able to find a inside z of I so that f of a is not 0. So this is what we want to do. So assuming that f is not inside the radical of I, we want to find a common 0 of elements of I, which is not a 0 of f. Okay, what does it mean that f of a is not 0? In a field, an element is not 0 precisely when it's a unit. So f of a not being 0, is equivalent to saying that f of a times something inside f is 1. So altogether, we are saying, can we find an n plus 1 tuple a comma b in f to the n, f to n plus 1, so that the first n terms, the first n components, give us a common 0 of the ideal I, and f of the first n components times the last one minus 1 is 0. So now I'm giving you a system of polynomial equations, and I'm asking whether or not this system of polynomial equations have a common 0. Now we are in the realm of Hilbert's Nullstellensatz version 1. So by Hilbert's Nullstellensatz version 1, we know as long as this system of polynomial equations generate a proper ideal, we do have a common 0 for them. So now in what ring of polynomials are we working? We are working in a ring of polynomials with one extra variable. So we have started with n variables. We added this extra variable. So essentially we are asking whether or not this system of polynomial equations, for every g inside the ideal, I look at g of x bar, g of x, I want to make sure that these are 0, and then I look at f of x times y minus 1, and I want to make sure that this one is 0. So I'm giving you a system of polynomial equations, and I'm asking whether or not this system has a solution in f to power n plus 1. By Hilbert's Nullstellensatz version 1, we know this system of equations has a solution precisely when the ideal generated by these elements, I, and this element, fy minus 1, in the ring of polynomials with variables x1 to the dot xn and y is a proper ideal. As we can see, y is different from the rest. So what I'm going to do, I'm going to think about this as a ring of polynomials where this is my ring of coefficients, and I'm mostly viewing it as ring of polynomials in terms of y. Okay, so we want to say that this is a proper ideal. But suppose to the contrary, it's not a proper ideal. What does that mean? This means 1 belongs to this ideal. What does that mean? This means I can find some elements inside I, multiply them by polynomials, add them, add a multiple of this polynomial, and end up getting 1. So assuming that this is not a proper ideal, we deduce that 1 is some element of I, f1, times some polynomial in terms of y, plus another element of I times a polynomial in terms of y, another element of I times a polynomial in terms of y plus fy minus 1 times a polynomial in terms of y is supposed to be 1. Again, f sub i's belong to ideal I, and these coefficients are inside this ring of polynomials. Okay, so now the key point is the following. This polynomial f is a non-zero polynomial. So after all, I'm taking this f to be not inside the radical. So f cannot be 0. If it is 0, then it is already inside the radical. So f is a non-zero polynomial in the ring of polynomials in n variables x1 dot xn. Notice that this is an integral domain. So I can talk about the field of fractions of this ring. So I can talk about 1 over f in the field of fractions of this ring, and I can evaluate, I view these polynomials in terms of y, and I'm going to evaluate both sides at 1 over f. I'm going to substitute 1 over f for y. The key point being that I want to get rid of this term. So I'm going to evaluate both sides at 1 over f. So what do I get? So again, 1 over f is an element in the field of fractions of this ring. Now I can evaluate at 1 over f. I get this evaluation map from the ring of polynomials with coefficients inside this ring with variable y. I'm going to substitute 1 over f for y, end up getting some fraction. So I give you a polynomial, you evaluate it at 1 over f. Instead of y, you plug in 1 over f. This is a ring homomorphism. I apply to the both sides of this equality, this one. I plug in 1 over f. What do I get? I get that 1 is f1. You see, f1 does not have any y. So when I plug in 1 over f, I do not touch f1. Only I plug in 1 over f for y. So I get 1 over f over here. I get 1 over f inside R2. And I continue like this. And I notice that f times 1 over f minus 1 is 0. So this term disappears. This term is 0. Altogether, we get that 1 is f1, R1 evaluated at 1 over f, plus f2, R2 evaluated at 1 over f, and so on, till here. Now, what kind of functions are these? So this is a polynomial with coefficients inside the ring of polynomials, and I plugged in 1 over f. If I take the common denominator of all the terms, if the degree of R1 is d sub I, then the largest power of f in the denominator is d sub I. So this means that R sub I evaluated at 1 over f is some polynomial divided by f raised to power d sub I for some integer d sub I. Now, if I multiply both sides by the maximum, f to power the maximum of d sub i's, what do I end up getting? You see, this times f to power n is a polynomial. So if I multiply both sides by f to the n, I get f to the n on this side is equal to f1 times some polynomial plus f2 times some polynomial, fk times some polynomial. All of a sudden, this power of f ends up being in the ideal generated by fi's. But remember, fi's are inside the ideal I. So that means f to the n ends up being, fi's are inside the ideal I. So that means f to the n ends up being inside the ideal I, which means f is in the radical of I, which is a contradiction because I assume that f is not in the radical of I. That gives me a contradiction, and that completes proof of the last version of Hilbert's Nullstellensatz. So it has many implications, but following maybe is one of the interesting implications of Hilbert's Nullstellensatz. So if F is algebraically closed, then every prime ideal of ring of polynomials is intersection of all of its maximal divisors. So this means all the maximal ideals that contain P. Okay, let's see why this is the case. We know that for every ideal I of Z of I, what does that mean? This is the set of all the polynomials that vanish at every point inside Z of I. So I give you a point inside Z of I, and then I ask myself, what are the polynomials that vanish at this point? And then I take intersection of them. So this intersection gives me all the polynomials that vanish at every point of this set. So I of Z of I is nothing but this intersection. But remember, Hilbert's Nullstellensatz, one of the versions, version 3, says that starting from a common zero of I, when I look at I of this point, I end up getting all the maximal ideals that contain I, all the maximal divisors of I. So this ranges over all the maximal ideals that contain I. So we get this equality. So I of Z of I is intersection of all the maximal ideals that contain I. But on the other hand, by Hilbert's Nullstellensatz version 4, the last version, this is nothing but radical of I. So we end up getting this equality. Radical of I is intersection of all the maximal divisors of I. Now I'm going to use this result for prime ideals. If I show that radical of a prime ideal is itself, I immediately get the claim that every prime ideal is intersection of all of its maximal divisors. But this is rather easy. So clearly P is a subset of its radical. Every ideal is a subset of its radical. Now we show the other way around. So suppose F is inside the radical. What does that mean? It means F to the n for some positive integer n belongs to the prime ideal P. But remember, prime ideal means if product of elements belong to P, then one of them should be inside P. So if F to the n is inside P, either F is inside P. So I write this as F times F times F times F times F. So one of them should be inside P. That means F should be inside P. So that implies that radical of P is equal to P, and that completes proof of this corollary. So every prime ideal in the ring of polynomials is the intersection of all of its maximal divisors. Okay, so let me finish by saying that it's not surprising that the picture in multivariable setting is much more complicated than the single variable case. In the single variable case, the common zeros of an ideal, if the ideal is 0, is the entire F to the n. If the ideal is not proper, then it's empty. Otherwise, it's just a finite set. It's the zeros of a single polynomial, and that would be a finite set in single variable case. And you can go also backward. If you give me any finite set, you can view it as common zeros of a polynomial. But when we go to multivariable case, then it's not as simple. In fact, many interesting surfaces or manifolds that we have seen are common zeros of polynomials, multivariable polynomials. For instance, you can think about a sphere. So here I'm thinking about real solutions, but the same is true for real or complex. So in fact, these kind of equations, we often want to understand not only solutions over an algebraically closed field, but also solutions over reals, over finite fields, over Q, and so on. So as I've mentioned, you can think about a sphere, you can think about n by n matrices that have determinant 1. that's an equation. So I'm looking at these n squared variables and I'm asking the determinant of this n squared variables to be 1. That's a polynomial equation. Or equation of this form, x to the n plus y to the n equals to 1, inspired by Fermat's last conjecture. Or equation of this form, x squared plus y squared plus z squared equals to x, y, z. This is related to so-called Markov triples, character varieties of punctured torus, and so on. And equations of this form, these are called elliptic curves. So there are many interesting equations, and this shows that understanding zeros of polynomials in multivariable setting is not that easy. But this geometric point of view gives us the needed language to ask the right questions. It helps us to use results from, geometry or topology, and it gives us very unexpected connections. So for instance, one can use this understanding of topological invariance over the complex solutions of an equation to deduce some facts about solutions of those polynomials over finite fields. So this is a deep result due to Dulin or Andre way before that. So anyway, so let's finish this course by this point that if you want to study these kind of things more, you can study algebraic geometry or arithmetic geometry or some parts of number theory. I hope that you enjoyed this course.